Is it recording? Yes, it is. So time check real quick. It's Monday the 30th at 2:30. So we're gonna do FRQ number 6. So let's just look at it real quick. A uniform spherical shell of mass m equals 5 kilograms and radius r equals 10 centimeters can rotate about a vertical axis on a frictionless bearing. So there's a spherical shell. You have a rope going over a pulley. Okay, and all the info for the pulley is right here, and then you have a block holding on right there. Friction. Alright. So part A, what is the speed of the object when it has fallen 80 centimeters from being released from rest? So our first step, we're going to have to find acceleration. So let's set up torque in order to find that. So actually before that, we should probably set up, find out what each of our tension is. So for this part right here, let's do it. I'm gonna be calling this tension right TH for horizontal and this TV for vertical. So remember, we're gonna start with torque equals I alpha. Let me just move it up. Torque equals to I alpha, and we're gonna be focusing on this right here. Let it focus. So if you expand that, that's going to be your tension H times your R is equal to the I value. Let me just write it out first. So if we expand it out, equals, and your I value for a sphere like a spherical shell is going to have a coefficient of 2/3 r squared, and then your alpha right here, we're going to expand it into just a over r. All three of these r's radiuses are the same, so we can just cross them all out, and your th ends up equaling to 2 over 3 m a. So remember that's going to be our tension horizontal. And then now we're going to find our vertical tension. So if you look from here, you can see it's we're going to set up Newton's net force equals m of this m right here, little m, a, and all your forces, you have F of G pulling it down, and what's opposing that F of G is your tension vertical equal to MA. Expand that, and you end up getting mg minus tv equals MA. Isolate for your tension vertical, move it to that side, move everything else to the left. Tension vertical equals mg minus MA. This is the part now where you set up torque for this pulley right now, which has these two opposing tensions to it. So let's set that up. So your net torque is equal to I alpha. So that's going to be T of, I want to put the T vertical in front, minus T horizontal. And then you have to multiply it by the R of the pulley. Remember that. And then that equals, so your I is already given as this number. Units for that would be kilograms times meters over second. Right? No, that is, no. Kilograms over meters squared. Yeah, it says it right there. And your I alpha your alpha right here, I'm just going to convert it to A over R as we did up here. Your A over R is R pulley. So we don't have the luxury of canceling out the R's like we did on top because there's no R right here. So what we're going to do, we're going to sub in TH there, TV there, and then just distribute all in and then group the common numbers. So TV is equal to mg minus ma minus 2 over 3 m big M A. It's encapsulated by R pulley equals 3e 3 units for that there times A, and this is all over R pulley. So what I would do next is distribute in the R pulley to each of the ones. And at this point, yeah, mg of, let me make sure you guys can read that, mg R pulley minus ma R pulley minus 2 over 3 m a R pulley equals 3e or A over R. At this point, I would start plugging in numbers that you can. So your mass right here, let me see what it was. Your small mass is 0.5 kilograms times your your gravity times your R pulley, which is 5 centimeters, 0.05 meters, convert, minus, again, your M is 0.5 kilograms. You don't know what your A is, so let's just leave it. And your R pulley, again, is 0.05 meters. Minus 2 over 3. Your big M is 5 kilograms. You don't know your A, leave it. And your R pulley is 0.05 meters. Equal to 3E. Your R pulley is again 0.05 meters. And then you have your A right here. So let's plug all this in the calculator. 9.8 times 0.05. This gets you 0.245. 0.5 times 0.05 minus 0.025A divided by 3 times 5 times minus 166A. That's going to equal to your negative 3 5.05 0.06, and then of course your A, and then let's add all the common stuff together. So these variable numbers with the variable A, we'll add them to the right. 0.06 plus 0.166 plus 0.025. 0.251A is equal to 0.245. 0.245 divided by 0.251. That means your acceleration is equal to 0.976. Just put meters per second squared. No, actually, that's not your answer. My bad. The answer was asking what was the final speed. So for that, what I would do is set up a common form. So you know your displacement is 0.8, I believe, meters. So if we do VF y squared minus V I y squared equals 2a. You start from rest, that cancels out. This is what you're trying to find right here. You know what your a is, we just found it, and you know what your delta y is, which is 0.8. So let's plug it all in. VFy squared equals 2, your a is 0.976 meters per second squared, y is 0.8 meters. So 2 times 0.976 times 0.8. VFy squared equals 1.56. But remember, we have to square root each side to get rid of that square. 1.56, 1.25, let's just call it. So VF equals 1.25 meters per second. And that's your VF after it traveled that much. I'm going to turn to this side. So now part B is asking determine the time it takes for the block to descend the 80 centimeters. So for this, I'm probably just going to use the position formula. So that's just going to be delta y, the initial velocity times time, plus 1/2 AT acceleration times your time squared. So delta y, you know that to be 0.8 meters. And for your initial velocity, you don't have any, so that would just cross out. 1/2 your acceleration we found on this side right here. It's right there, 0.976. 0.976 meters per second squared, and then t squared. So let's isolate for the t by first multiplying by 2. 0.8 times 2, and then let's divide it by our acceleration, 0.976. So I get t squared is equal to 1.639 square root to get rid of the square. And for my time, I got t equals 1.28 seconds. Alright, so that's part B right there. Part C, determine the sphere shell's rotational kinetic energy after 80 centimeters of the cord has been unwounded. So to find the rotational kinetic energy, KE rod basically, it's just 1/2 of your moment of inertia times your angular velocity squared. So let's actually break up the I real quick. So for the spherical shell right here, your moment of inertia would be 2/3. And then, because I would be equal to your coefficient times mr squared. So 2/3 is your coefficient. The mass would be 5 kilograms. And then the radius would be, it states right there, it's 10 centimeters. So 0.1 meters. And we have to square that. So let's just plug that number in real quick. Times 5 times 0.1 squared. 0.03. 0.03 in there. And of course it's your I, so it's kg squared. And then for your angular velocity right there, remember the formula V equals WR. So I shouldn't say W. Angular velocity is equal to V over R right there. So let's see. Your V was 1.25. So it'd be, let me move this up. 1.25 over meters per second. And your R, in this case, because we're doing it for the sphere, would be 0.1 meters, 10 centimeters. 1.25 divided by 0.1. And then you would square that. Alright, so this is your angular velocity. 1.25 divided by 0.1. 12.5 rads per second, and you have to square that, remember. Square times 0.03. So you get around, wait, hold up. Let me just check if I got all my numbers right. 5 times 2 divided by 3. Times 5.1 squared. And then for that, I multiply by 12.5. Yeah, you get around 2.6. Yeah, it was just rounding error. So that is what I got. So that be in joules. And then your last part, what fraction of total energy has been converted to the pulley? So let's just do your KE rot of the pulley first. KE rot of the pulley, 1/2 I omega square, 1/2 your I, it already gave it to you, right? KGM. And your omega square this time, same thing, omega is equal to V over R, velocity over your radius. So this is going to equal 1.25, and then this time your radius is going to be 5 centimeters. Meters per second. 1.25 divided by 0.05. Got 25 squared, remember, square it. 3e times 25 squared. 0.94 is your kinetic energy rotational for your pulley. Now let's find your overall kinetic energy, and that would be so you just use your potential energy, because all the movement from your potential gets converted to your kinetic as it goes down here. So all you really need to do is find your potential energy. So all that would be is your KE total would be equal to your PE is equal to your M, little m, GH. Your mass was 0.5 kilograms. G is a constant, and H, you went down 0.8 meters. So it'd be 0.5 times 9.8 times 0.8, 3.92 joules. So we're trying to see how much of the kinetic energy from the total got converted into the pulley. So if we just divide that over that, you get 0.94 divided by 3.92, 0.239. Let's just say 24% of the total KE went into the KE rod pulley. So that would be your answer for part D. Oh, and the time, it's, I don't know if you can see it, it says 2:50.